It's a great honor, great pleasure to have opportunity to share some of our work here in the transportation in the area for generative hyperheuristics for the transportation problems. So as Dr. Mi said earlier, my name is Ruibin Bai, professor in the School of Computer Science, and we have a research group called the Artificial Intelligence and Optimisation Group. So in this group, I think our unique strength is combining AI, computational intelligence, and techniques from the operations research. Again, it's a heavily popular or heavily used technique in transportation problems in the combinatorial optimization. Additionally, we are collaborating with Ningbo port. So we have a digital port technologies lab. And right now, lab has about 20 academics, about 50 PhD students. Of course, about a third of them working on the optimization, AI for scheduling for optimization, but there are students working in computer vision, some business analytics, etc. So it is a great pleasure. Thank you. So today I would like to share our work on the generative hyperheuristics for the online transportation problems. So this is a work has deep motivation from industry. So it's pretty much problem-driven research. So I'm going to start with the motivation of the research, the real-life challenges that we face for the transportation problems, and while we look at generative methods to address these challenges. And then I'll follow that with two categories of the methods. One is called deep reinforcement learning based hyperheuristics, and they follow with a more recent work on the genetic programming and its ensemble version of the hyperheuristics. Finally, I have several real-life problem examples that we have conducted using similar ideas or similar paradigms, but depending on the time, I might share one or maybe two. Okay, so we are in the era of AI. There's huge opportunities in virtually every direction or every industry you are talking about. The application be used to transform that industry, right? So things like transportation, smart factory, smart logistics, smart city, aerospace, port, hospital, railway station. I mean, all these are classic application domains that could have a profound impact on our daily life, right? How can we transform the latest AI technologies to help transform the business in these sectors, right? So we have like a rough classification of these applications. So you see, at the perception level or understanding level or decision making, right? So I think there were recent remark last year from a top scientist about although the application of AI in many industries has been prevented, but really many of them are still at the supporting role level, and helping, AI has been used to help find better perception, classification, diagnosis, right, to help us develop better understanding from a huge, from a complex systems. But there's a very rare application, or there's still very limited application in terms of making best decisions, using AI. So I think for all of the researchers working in the computational intelligence, I think this presents a great opportunity for us to really, after many years of work, this is really an opportunity for us to have meaningful impact in these industries, right? So using the latest AI to help industry to make smarter decisions, right? More optimal decisions, to help them to optimize their resource allocation, to optimize, to reduce the cost, to improve the efficiency. I mean, that's a requirement from every industry. However, right, so when you talk about real life systems, in many cases, you know, perversely, I think predominantly in a computational intelligence society, there are so many people paper or research have been working on deterministic problems, right? So in this setting, you generally assume a very stable system that the parameters and the development of the system can be predicted, right? So you know, although the challenge still is huge because of the size of the search space, because of the decision making involves maybe it's multi-objective, etc. But generally, you would assume that system can be predicted in a way. However, in many other systems, in fact, all the examples I talked about earlier, particularly in the transportation domain, you have a system that evolves some uncertainties, right? So that means you're able to predict the system behavior to a certain degree, but there are always factors that are not 100% certain, right? So that means you have what we call limited predictability, right? So in this case, when we have uncertainties, the problem challenge that we face is going to be much, much higher. So today, our work is focusing on the left side, you know, the system, complex systems where you have limited predictability, right? So the main characteristics or main challenges of this kind of system, decision making in this kind of system is basically the scale of the problem still very large. Sometimes may involve multi-objective optimization. You have very complex, sometimes nonlinear constraints. And more importantly, I think this is a killer challenge that you know, system always evolve some dynamics or some uncertainties. Okay, so in the case of a complex system with limited predictability, how do we handle them, right? Okay, so for people who are working with deterministic problem, they'll say, well, okay, we can still do this with often with what is called a rolling horizon, right? So you plan, right? So what you do in this problem-solving paradigm is you start with a problem parameter estimation, right? So you have a problem, you basically use whatever tools available to estimate the parameters of problem. That could be the travel time, that could be the machine processing time, that could be demand for particular products or services. That can be estimated, right? So based on the estimation, you construct a deterministic problem model, right? And that model, once that model becomes available, you can develop the optimization algorithms, right? So generally, you know, you have you know, problem, you know, from community in operations research, they would have you know, they would try to find a way to formulate the problem in a nice way so that the model can be solved to optimality. And I think in CI community, in many cases, you know, we are trying to find a near optimal solution using the heuristics, use the meta heuristics, or some learning-based method, right? So the output of this is a solution. They based on this solution, we develop a execution module, right? So that solution get executed or implemented, right? So in the event of uncertainty, right, with the rolling horizon, basically what you do is that, while the solution is being implemented, you continuously monitor the difference or the gap between the estimation you had earlier and at the actual realization of the uncertainties, right? If the prediction based on a deterministic model at the actual realization, the gap is too big, you could basically, let's try to resolve the problem, right? So then you restart the optimization and then that returns a new solution, right? So use a simple VRP pickup problem as example to illustrate the process. So what you do is basically you say you have a depot, you have a number of vehicles, you have a number of customers, those nodes, that you need to design the cost effective or the minimum a vehicle routing plan with minimum cost, right? So what you do is say, well, let's try to estimate the cost, right, between any two nodes, right? So similarly, these are the numbers, arc from node, this node to here is 5. That's the estimation. It could be, whatever you measurement you use, and they for each customer you estimate the demand from that customer, right? So in this case, assume that, for this particular customer, the forecast demand is 10. However, as I say, given the uncertainties, there's always errors with your estimation. So assume that this is your forecast number, that's the actual realized demand, right? So the number in the bracket is the realized demand, right? So when you come up with a very complex mathematical model like this, I mean, in the operations research, usually you would model this either on the left side, basically it's a flow based optimization model, or the right side is a set covering model. I mean, these are the mathematical model you can put in the commercial solver, with some clever tools you can solve it, or you can use the evolutionary algorithm or the GA or some others to solve these, to come up with a solution. I mean, so here assume that these are the vehicle routes that we came up, right? The problem is that the optimization is based on the forecast number, and with uncertainties, the routes that you produced based on the estimation data could have problems, right? So here, for example, this particular route, because the errors you have here at estimation errors you have here, so you would have a profit drop because of the optimistic forecast, right? Because here the forecast was too optimistic, right? So that has a big drop in terms of profit. For another route here, it actually leads to a feasible solution, and the last node cannot be served simply because of the estimation. You underestimate the demand, right? So for this particular, or the optimization was too, you optimize the route to the limit, really. I mean, so there was a sense of over optimization, and that lead under the assert environment that leads to a feasible route, right? So you can say, well, okay, whenever you have run to a problem where there's a feasible route, let's just stop the system, re-optimize, right? That is fine, but you have less dynamic. I mean, the estimation error is not huge. However, when you have too many dynamic events, you may lead to multiple resolving the final solution quality drop because of the things like this, right? So generally speaking, with this, the deterministic model with the rolling horizon, you often have a strong assumption at the beginning using the historical data, but it cannot exploit the sequentially revealed new information, and the optimization tends to be over optimistic, right? Because you are too confident with the future returns. So what we need to find out new ways to address the uncertainty, right? More effective ways. Okay. So what would be a desirable characteristics for this optimization algorithm, right? So first, we got to find a way, more flexible way to handle the dynamic events. Okay, right? So previously, I think particularly, these dynamic events could occur multiple times, and that leads to a very ineffective way with a rolling horizon. So we need to find a better way to do it. Second, right, if we plan to apply this to the industry, you got to find a way to interpret your solution, how the problem is being tackled, right? So there needs to be certain level of interpretability. Thirdly, the solution must be general enough, right? So that means that your solution needs to handle multiple scenario cases, right? That means the algorithm must be able to handle multiple distributions of the randomness, right? Not just a simple single constant or stationary distribution. You got to be able to handle multiple distributions. Finally, right? So algorithm design is very I think it requires a lot of knowledge, expertise, right? So, ideally, the algorithm can have certain level, algorithm design can be automated to a certain degree. Okay, so these are the sort of like four main traits in my opinion. But of course, ideally, there's some others depending on the different industries. Okay, so here is a alternative paradigm to handle the uncertainties, something what I call the constructive solution or constructive or generative solution methods. So previously, this is the way, what we call like deterministic problem solving with resolving, with rolling horizon resolve. Here, what we could do is instead of producing a solution to be implemented, what we could do is to use the machine learning or data-driven methods to develop a optimization policy. And that policy can be reused multiple times to construct or generate a solution, right? So the benefit of this are as follows. First, you do not have to estimate the parameters, right? So that, instead, estimated the problem parameters directly, what you could do is to estimate the distribution of the parameters. So from the beginning, you would assume that the problem has uncertainties and the parameters are subject to change. But what you need to do is just using the historical data to estimate the distribution and use that to create your training data set. And then you construct a stochastic problem model, and they use the learning, latest learning, machine learning, or learning-based optimization to produce or output a optimization policy, and that policy be used, to construct or generate a solution. So it's a generative solution building. It's a learning-based approach, right? And you don't have to estimate distribution of the random variables. sorry, you don't have to estimate the exact value of the randoms. Instead, you only need to estimate the distribution. Okay. So, I mean, we have been working with multiple real-life examples, including the city logistics, the supply chain logistics, some problems in Ningbo port, right? Both the cross-terminal transportation or transshipment problem and the transportation problems within a container terminal. So all these, we had fortunately, we were able to gather some real life data, so we can test our algorithms with this real life, setting. Okay, so what we did is, I'm going to present two main classes of the methods. One is the deep reinforcement learning based hyperheuristics, and followed with genetic programming based hyperheuristics. Okay, so I don't know how many of you are familiar with the hyperheuristics. So it's really a work pioneered by the group of researchers in Nottingham, UK, many years ago. I think the first paper was drafted in 2001, published in 2002. So the time that I only had an opportunity to join Nottingham. So basically, there was over 10,000 papers on Google Scholar or hyperheuristics. And it's basically a class of optimization methods with a common goal of automated design and tuning of the heuristic methods, right? So the algorithm framework aims to promote generalization, cross-domain, cross-scenario algorithm performance, and also hopefully to automate the algorithm design altogether, right? So one central idea of this hyperheuristic is actually you are dealing with two search spaces. So generally with non-hyperheuristic methods, you try to search within the solution space directly. But with the hyperheuristics, you aim to search within the heuristic space. Okay. So there's lots of challenges with hyperheuristic research. So here in this diagram, all the you have a heuristic search within the heuristic search space, and there's also each of these little asterisk represent a low-level heuristic or some simple rules designed for a specific problem, right? So there's a research can be focused on a high-level strategies, how to select the most suitable heuristics for the given problem, and lower level you want to come up with a repository of lower level heuristic policies that can adapt to different problems, adapt to different distributions, and that can be reused multiple times, and it can extract the knowledge from the experts with some good interpretation abilities as well. Okay, so I think at both levels, I believe still there's still a lot of recently there's a lot of exciting development, I think, in both levels. So in our research group, we aim to focus on try to combine our expertise in the operations research, and of course, like Dr. May, we have a strong interest in evolutionary learning, and we also work with deep learning, particularly in the form of deep reinforcement learning. So hopefully, with the combination of the techniques from these three different domains, we're able to construct a solution that satisfy the four traits we mentioned earlier. Right. So let's start with one of our initial work we did. I mean, a simple deep reinforcement learning for the combinatorial optimization. So I'm going to talk about the actual problem later on when I share. But the key idea here is actually we want to build, right, a simulator, right, environment, simulation environment that mimic the complexity of real life problem, right? So instead of basically using some simple functions to represent the quality of the solutions, we get to build in the complexity of the real life problems, right? So in this particular truck dispatch problem, we would build in the physical components, the road network, the yard, berths, area size, equipment capacities, as well as the business constraints, right? And some uncertainties in terms of the service time, traffic congestion, the truck speed, etc. All these, the data being populated into the simulation environment. And we believe that once your simulation environment, can better capture the key characteristics of your system, you have a better chance to train a agent that can make better decisions, right? So this is the early work we did. The main ideas is a real-to-sim simulation-based DIR method, right? So of course, like many DIR methods, I mean, you would have to spend a lot of time to study the problem, to come up with a good set of features and that try to capture the characteristics of problem, and they hopefully with a good design of the value function, reward function, we hope to come up with a good deep learning model. All right, but in many cases, it's actually not very easy. So you have to use additional tricks, right? Try to use, for example, here in this example, we use the expert network, try to stabilize our training at the initial stage so that the system can be converted to something, a more stable network at the beginning, so that you don't waste lots of time to do the exploration. All right, so in total we have about 10 features for each queue. Queue basically is represent the number of machines, the critical machines. In this case, the key trays. Right, so each key tray has about 10 parameters to capture its states. And if you have 20 machines, that's 20 times 10 feature vector fed into the network. The output is a particular decision for that particular state. Okay, so that's the initial work. Later on, we try to build this with the hyper-heuristic framework. So instead of asking the DIR agent to directly output the action, right, suggest the action, what action to do, what we do is that replace these actions with human understandable heuristics, right? So these heuristics 1 to n, these are the heuristics that can be designed by experts, right? In fact, I think one of the heuristics, actually, it was a joint work between our lab and the people from the port. I said, well, we have been using this rule for many years. I think under normal circumstances, this rule works very well. Okay, so we basically, developed, I think, 6 or 7 different heuristics, using, trying to parameterize that particular heuristics so that to generate multiple heuristics for the hyper-heuristic for the deep reinforcement learning to choose from and as actions. And the MDP model we have, of course, what we observe state, because we have we're able to have partial solution states, explicit partial solution states, but also you can have some model-derived solution states. So that is based on some mathematical model that you can have about the problem, which can better capture the features of the problem. Okay, so but I mean, this was very early work. Network wasn't very advanced, but it produced about 5% improvement compared to the late human desired expert rules. But we face a lot of challenges with large action space, and there's a sparse reward. So there's a limitations with this work. So through these two work, we were able to somehow handle the uncertainties well, because the solutions only solutions are built gradually, and therefore you're able to exploit the new information that revealed over time, right? And also with deep reinforcement learning hyperheuristic, we're able to interpret the lower level heuristics or rules. I mean, these can be understood by the experts, by us. However, generally, in terms of cross scenario, cross distribution generalization, there's a limitations. Often when you train your DIR or one distribution, and if you test it, you would observe quite substantial drop. If you train your algorithm on a particular problem size, it would drop, for a different size. Okay, and of course, with the algorithm, we have to design, right? Particularly with the previous hyperheuristic, we have to manually design the low-level heuristics. Okay, so can we do better? Try to address this cross-scenario, cross-distribution generalization issue, and can we upgrade or can we up the level of the algorithm design automation? Okay, so that leads to our two recent work based on genetic programming, right? So we believe that natural evolution has the advantage because it's robust, has been proven, with billions of the years, and can balance the complexity, reliability, and efficiency. I mean, very rarely you see a species would die just because of the temperature change in the environment or some sudden events. Usually, I think, even the human being, COVID is one example, right? So you're able to adapt to the different changes. So in this particular work, what we did is, again, it's a GP, but we have this what we call the double layer genetic programming. So we have what we call the scenario layer, and we have a utility calculation layer, right? With these two layers, we are able to deal with these multiple scenarios, right? Because to develop, to evolve a tree that can work well across so many different scenarios. It's not easy, right? We use some simple step functions to test this, and you can see that the traditional GP does not work very well. I mean, even with more advanced techniques, still you see at some sections it does not perform well. So with this carefully chosen features or terminals, about again the same terminal state features we use, and this double layer GP produce a better performance across multiple scenarios. Okay, sorry, that's this is the general. I mean, we didn't use any fancy techniques in terms of crossover mutations, just standard GP, but with some novelty in terms of solution encoding. And the second work extended the previous work by combining the GP agent with a deep reinforcement learning agent. Okay, so in the GP agents, often you evolve a population. The final performance of the GP is evaluated by the best individual in the population. Right? You pick the best one, and the rest will be, thrown in a bin, right? And so it's not used. What we had here is actually, why don't we try to combine multiple individuals in the GP, because each of them may have different advantage for certain scenarios, right? So can we combine them together? So what we did is basically, this is two-step method. We first use GP to train multiple heuristics. Each heuristic have a different characteristics, and we put them together with a deep reinforcement learning framework. And then so the action in the DIR is not the actual problem action, is actually the action is a combination of the heuristics, right? So what we did is instead of try two schemes. One scheme, basically we ask DIR to pick the best heuristics, a bit like work we did earlier, but instead this time the heuristics are automatically evolved by GP. The second scheme basically said, well, actually for any decision we want to combine multiple heuristics to make a joint decision, right? So this is a simple way using weights to combine. It's like a voting, but with some learning within the DIR framework. So these are the sort of the results. In the end, you can see that generally the DIR hyperheuristics, and these are the manual heuristics, basically the expert rule. And you can see that the DIR hyperheuristic, generates a fairly good improvement of 7%, the 8%. But when we combine them together with the ensemble, that produce significant improvement, like 70%, 74%. Right? So building the ensemble really helps to improve the performance, particularly where your test data set involves multiple scenarios. So with these two recent work, I think we are able to handle the cross scenario, cross distribution issue to a certain level. I would claim that we solved the problem, but still generalization for DIR still remains a very big challenge. But we improved the previous performance, and also because both the high level stage and the lower level stage are automatically trained, so it helped us to improve the algorithm design automation. So algorithm can be automatically trained without human intervention. Okay, so I have about 10 minutes to go through some of the real life examples we had. The first example is the container port. Thank you. Yeah. So as I said, in a container port, three types of key resources you want to maximize the utilization. One along the coastline is called a berth. Basically, you have a fixed length, and therefore you have to carefully allocate the berth. And along the berth, you have a key crate. Each machine costs millions or tens of millions nowadays. So it's really expensive, and their efficiency represent the output of the container port. On the land side, again, every piece of land is very expensive. There's a limited space here, so you got to use the land space very well, because containers are stored temporarily, right? So this is a more or less like a warehouse. But with huge machines to lift and drop off containers. And then between the left side and C side, you have this big truck, basically connecting the operations between C side and left side, right? And these are the ones that we need to schedule, because they are the ones connecting the operation between left side and the C side. If you don't schedule them well, that leads to huge efficiency issue. So in fact, there's so many different problems, combinatorial optimization problems. So today, the example we are using here is just the truck routing and the scheduling or dispatching. There's other like a container stacking, burst allocation, crate allocation. I mean, that's separate. But these problems are interlinked with each other. So that shows the complexity of these kind of problems that you try to deal with. Right? So so this is the real life problem. We know the data from the port we collaborate with. You can formulate, come up with some kind of like a formulation. But it doesn't matter how hard you work with. I think with the port that we collaborate with, the reality is actually there's a lot of uncertainties here, right? Some of the uncertainties are internal. Maybe some drivers are faster than the others. Some days when the weather were good, the cranes work faster. Some other days, when it's windy, the operation is very much slower, right? And there's delays with the ship. There's interruptions from the external trucks. So uncertainties are inevitable, right? You have to build your system to handle these uncertainties, right? And also because of this problem, you see each transportation involves 6 operations, and these operations are interlinked. So there's a high correlation interdependency in the system. And if there's a one change or one error at the beginning, the error would be magnified later on. So that leads to a very unstable situation. And plus, the scale of the problem is very large. There's some queues, which makes the problem non-linear. So traditional deterministic method often would fail, right? So we got to look for a methods that can handle the dynamics, right? Like the one that we introduced earlier. All right. So these are the results. I'm gonna skip these two actual results. I have maybe 1 or 2 minutes. I'm gonna show you briefly about 2 other problems. So sorry. By the way, these methods, particularly the early 2 methods, they have been deployed in the actual productions. The most recent ones we haven't got opportunity to deploy them in a production, but early versions have been used by some of the container terminals. The second example is the Huawei pickup delivery problem. Again, this problem have a huge uncertainties, very complex constraints in terms of pickup delivery. Basically, the first kind item in, last time out, and you have to it's a multi-objective optimization. There's a very complex rule to compute the objective function. So again, traditional deterministic model cannot handle this. So we used a framework called basically we combine the evolutionary algorithm and reinforceable learning to help us to address huge search space, state action space, and in the end we were able to produce results that are much better than the defining, right? So originally student they got 6th place, but with the latest development, we were able to achieve significant improvement compared to the original version. These are some of the visualizations. We recently also worked with a AMR, basically is like AGV used in a warehouse that allow you to transport the packages between different parts of the warehouse to service the demand. Again, the main novelty of this is a combination of the DIR and genetic algorithm, but this time we have it's a Bai agent basically because of the planning horizon and the planning period at the strategic level, at the tactical level, they're different. So we have to use a multi-agent system to address this problem. Again, we made some progress in terms of result. Okay, so very quickly to conclude, so we believe that the operations research, I think many combinatorial optimization problems have a nice structures. It would be good that we are able to exploit these structures, in terms of constraints, in terms of objectives. I mean, if the problem can be formulated very nicely, and we need to exploit these structures. I mean, generally, if you just rely on the OR method alone, the resulting solution may not be robust, and the computation of these solutions are very expensive. If you want to use robust version, like a robust optimization or stochastic programming, time becomes ridiculous. So I think learning assisted methods, particularly in terms of the generative learning-based methods in the framework of hyper-heuristics, can potentially balance the performance and the robustness, right? We've shown that by combining the reinforcement learning and genetic programming, that can demonstrate the great performance boost and the generalization ability, but also it can improve or enhance the algorithm design automations level, right? So because of the a lot of the heuristics can be learned or trained through the system. Okay, so generally, I think the hyper-heuristic is a good framework to use to handle different challenging combinatorial optimization problems, because you can reuse the method that you trained before, and also to provide better interpretability. Okay, so that's all concludes my talk. Thank you very much. Thank you.